Hello guys, I'm back. Today let's answer the following question. Is the total number of stage of equilibrium in a tray column the same as the number of trays in this column? My name is Jeferson Costa and I teach students, graduates and engineers how to work with chemical process engineering and plant design. Follow my profile and like this video to have hundreds of contents related to chemical process engineering and plant design. As a chemical process engineer working with plant design, eventually you will find yourself with the task of sizing selection in doing the selection of a distillation column. A distillation column can be a trade column or can be a package column. But for this video, let's focus on the trade column. So to start with the calculations for sizing selection, you must have the product specification, the raw material conditions, and you will do the calculations to verify what are the total number of stages of equilibrium between vapor and liquid of your feed stream to get the specification, the required specification of your product based on the conditions of your raw material. And there are many ways to do that. One of the ways to do that is using the Macbeth-TL method. That is a graphic method where you find what are the maximum or the total number of stages of equilibrium. This method will give a number to you. For instance, 10, 15, 20, no matter, it will depend on the feed conditions and the product specification. Once you have this information, most often, when we are talking about chemical process engineering and plant design in design companies, not in the university, not in the college, but in real life in plant design, you will not do this kind of calculation as hand calculations. You will usually use a process simulation software to perform the calculations because as complex is your process, it gets more time to be converted, and because the companies needs to improve the efficiency of the work. So based on that, you will probably use a process simulation software. Here in my screen, you can see the Aspen High C. So I will use the Aspen High C to let it easier to illustrate what I have here to teach you or to share with you today. So when you get the total number of stages of equilibrium from a shortcut method, you need to add that now to a detailed column in your process simulation. Here, for instance, I used a standard distillation column from Aspen High Seas, and per standard it comes with 10 stages with a reboiler and a partial condenser. So if your calculations, your preliminary calculations for the total number of stages have given to you a number of 20, let's suppose it's 20, what is the number of stages that you will add to your process simulation to start correctly doing your job as a chemical process engineer in plant design? If your first guess is that you will add 20 to your distillation column, you are not correct in a not correct direction, because the Aspen High Seas do not add to the total number of stages when in this section here the stage of equilibrium related to the reboiler, and do not add the stage of equilibrium related to the condenser. So when you have a distillation column with a reboiler and a partial condenser, each one of these units or each one of these sections represents one stage of equilibrium vapor liquid. And you can verify that because you enter with liquid in the reboiler and you have addition of energy, and you are able to have a stream that is vapor and another stream that is liquid. So it represents one stage of equilibrium in your distillation column. If you take it into account now, right now, instead of having 20 20 stages of equilibrium. In this distillation column, we have 20 stages of equilibrium plus 1. We have, in fact, the total number of 21. But we need to verify also the condenser. What is happening in the condenser? The partial condenser, I have a vapor stream come to the equipment, and I only do the partial condensation of this stream. So I have equilibrium stage with vapor in liquid where my vapor phase is withdrawn as product, for instance, and I have a liquid stream that part can return as a reflux and part can be removed as distillate. So in this case, I have another stage of equilibrium. So summing up 20 plus 1 in the reboiler and 21 plus 1 in the condenser, in the partial condenser. Here, in this case, specific case, I have 22 stage of equilibrium or 22 total stage of equilibrium in this distillation column. So in this case, my number of trays is 20 because I have set 20 in the number of stages, but the total number of stages of equilibrium is 22. So if I need 20 stages of equilibrium as a total, what I need to do here is to discount the stage of equilibrium related to the condenser and the stage of equilibrium related to the reboiler. So instead of using 20 as the number of stages, I would use 18 as the number of stages. So in this way, I have 18 trays in my distillation column, but I have 20 stages of equilibrium in my distillation column. But there are something to observe also. Eventually, your condenser is not a partial condenser. It can be, for instance, a total condenser. And in this way, I don't have anymore, or I don't have the splitting or the equilibrium between vapor and liquid in my condenser, because now I am condensate everything at the top of the distillation. So now I don't have more a stage of equilibrium. And if I keep my distillation column as 18 trays plus 1 reboiler, I will have a total number of stages of equilibrium of 19. And it is below my required total number of stages of equilibrium, that is 20. So in this way, if I using a total condenser, instead of using 18 trays to my distillation column, I would use 19 stages my distillation column, and the number of stages in the Eisenhower series here represents the number of trays, but it is not necessarily the total number of stages of equilibrium that you need to your process. This concept is very important, guys, because when you are doing chemical process engineering plant design, we are talking about doing specifications, documentations to have equipment erected and installed in the field. And as you increase the number of stages in a column, you are increasing the size of the column, and because of that, you are increasing the capex of the column and not necessarily improve the requirements for your product specification. So this is a very important concept and basic concept that you must be aware when you are doing your process simulation for plant design. If you want to know more about chemical process engineering in plant design, take a look in the next video that will appear to you right now. Share this video with your friends, students, graduates, and engineers to help them know more about chemical process engineering in plant design. That's it. I hope you like it, and I'll see you soon in the next video. Bye bye.